Hi, everyone. Welcome to the Power Hungry Podcast. I'm Robert Bryce. On this podcast, we talk about energy, power, innovation, and politics. And I'm pleased to welcome a new friend of mine, Rusty Towell. He is a professor in the Department of Engineering and Physics at Abilene Christian University. He's also the director of the Next Lab, which we will talk about momentarily. Rusty, welcome to the Power Hungry Podcast.
Thank you. Appreciate you having me.
I warned you. I don't warn all the guests, so you can be glad about the fact that I warned you. Guests on this podcast introduce themselves. So imagine you've arrived somewhere. You're not in Abilene anymore. You got about 60 seconds. Introduce yourself, please.
Oh, thank you. My name's Rusty Towell. I'm a professor of engineering and physics at Abilene Christian University and director of the Next Lab. Next stands for Nuclear Energy Experimental Testing. We are focused on making the world a better place by addressing some critical needs in the world by developing molten salt reactors. And so I get the privilege of leading about 150 people in this effort to achieve that.
Well, okay, so that's great. Well, and that's why I wanted to have you on the podcast to talk about this project of the molten salt reactor. In last August, the Abilene Christian applied to the U.S. NRC, the Nuclear Regulatory Commission, for a construction license on this reactor, which is reportedly the first application for a new U.S. research reactor of any kind in more than 30 years, which by itself is a remarkable fact. But why Abilene Christian? Why now? And is that true that this is the first research reactor in 30 years? I mean, that's a pretty stunning fact in a time when the U.S. is trying to get back in the game in nuclear power. So what's going on?
Yeah, so the number of research reactors across the nation has been on a steady decline for decades. We've decommissioned quite a few, but haven't had any new come online. And so the last reactor to come online was, I guess, University of Texas when it moved from sort of its downtown main campus up to its research campus, still in Austin city limits. But that transition, happened over 30 years ago. And so if you're talking about a brand new license for research reactors, it's been even longer. And if you're talking about a non-water cooled research reactor at a university, that's never happened. So we're sort of plowing a lot of new ground here.
Excuse me. So I know. So what you said, that reactor moved from what was the 40 acres. I graduated from UT Austin. I know you got your PhD at UT. I just looked you up as well. So that when they moved that research reactor to what's now called the Pickle campus, that was the last one. You're saying, but so now we have the potential for another research reactor here in Texas. So why Abilene Christian? Why is this happening there? Forgive me, but when I think of new research reactors, I'm not thinking Abilene first. So why Abilene and why now?
Yeah, that's a great question and one that I think it deserves answering and people understanding. Several things came together. I'll just say the right people, the right conditions came together to allow it, and I think that it's a great choice. One thing is ACU is a smaller university, and so is able to be a little more nimble and quick. Also, this is a very interdisciplinary project, and so being a little bit smaller in size, it's a little bit easier to get different disciplines. And I'm not talking about maybe a mechanical engineer talking to a nuclear engineer. I'm talking about, can we get chemists and physicists and engineers all to collaborate together? That's something that is a little bit easier at a smaller institution. But probably the biggest reason is because the university leadership believes in the project and supports it. And Natura Resources founder, Doug Robinson, believes in this project and believes ACU is the right place to lead it. And so because of the support, I think that allows us to move forward.
Well, so I want to come back to Natura in just a minute, but I live in Texas. I've been through Abilene. I haven't been to ACU's campus. I hope you invite me sometime. But how many students at ACU? It's a private school. What's the tuition? And how many faculty are potentially going to be working on this project at ACU?
So ACU is about 5,600 students total. There's less than 4,000 resident undergraduates on our main campus in Abilene. We also have an ACU Dallas location, a lot of professional online courses. But the ACU campus in Abilene is just under 4,000 students. Right now, we have about 8 faculty involved with the project, a total of 30 faculty and staff. During the summer, we're able to pick up additional faculty that'll join in the effort. And so we probably have about a dozen faculty that are or have been working on the project over time. We hope that number grows. The university is looking to grow a nuclear engineering program. And so as those different academic programs grow, obviously the number of faculty involved will continue to grow also.
But the next lab project itself and the reactor project, you have other partner universities. If I recall, it's UT Austin, Texas A&M, and Georgia Tech. How did that come about? How did this consortium come about?
Yeah, so we refer to that our research alliance, our next research alliance, or NEXTRA, and all 4 universities have sponsored research agreements from Natura Resources, and so that's sort of the formal forming of that. Informal discussions between faculty members at the 4 institutions date back years, and so as faculty like to dream about the future and think about collaborating on research projects, there's a lot of discussions, and so for years we had informal discussions before we understood or had a funding path to enable it. And when Natura Resources stepped forward as being the prime funder for this, then formal sponsored research programs were put in between all the universities and Natura Resources, and that allowed the formation of this research alliance.
And so those other universities, then they will have students and staff or student and faculty that will come to Abilene then to work on. I mean, I'm thinking just out loud here as I'm riffing here, but it sounds a little bit like a telescope project, right? Where you have a bunch of different entities that are part of a group that will allow their people to come and participate and use the telescope, do research. Is that a fair kind of a comparison on a project like this? Because it's a big capital project, no?
Absolutely. And that's exactly right. I mean, obviously, there's a lot of work that can be done remotely. And so we benefit from work that's done on all 4 campuses. But we have had guests come and work here, students come and spend the summer working with us. And we look in the future for that to happen more and more often.
And so, sorry, I'm just adjusting one quick thing here. So, what is going to be the capital cost of the research reactor? How much is that plant going to cost, and where are you in terms of the? I understand you've already started construction. You applied for a construction permit, but I understand dirt's already moving.
That's right. So one of the things we like to do is we like to do as many things in parallel as possible to move forward in a timeline that allows us to really get this deployed to the world, right? I mean, you don't bless the world if we just have an R&D project on a university campus. We really have a chance to really make an impact in the world if we can take this technology and deploy it. So we're really looking forward to that. And so we like to do things in parallel to give us the shortest timeline possible. And so while we have submitted an application to the NRC for a construction permit for the research reactor, we have started construction on a building to house that. And for a commercial reactor, this isn't an option. You can't start a building for a commercial reactor until you have a construction permit for that from the NRC. But for a university research reactor, there is provisions in the licensing code to allow you to apply for a license to build a reactor in a multi-function pre-existing building. And so we are building this building that will be pre-existing when we get permission to build the reactor. And so we've separated the physical building from the reactor that's going to go inside of it. And that's something, again, that's never been done before, but we're excited about having a building that will outlive one research reactor.
And so what is the capital cost here, Doug or Rusty? What are you saying? What is this project going to cost?
So the building, Abilene Christian University is investing $23 million in the building, this multi-use facility that will house the research reactor. The actual reactor itself has a price tag of about $100 million. And then on top of that, there's the cost of fuel and operations. And of course, no use building it if you're not going to operate it and do some research from it.
So I get the cost of the building. $100 million for the reactor. So where is that money going to come from?
So Natura Resources has been funding it and will continue to fund it. Obviously, something this large, it would be nice to have support from other entities. And so we are actively, looking for sources, both federal dollars and state dollars, to help support this. And we believe this is the type of stuff that both the federal government and state governments are interested in and have funded. So we're looking for other sources, but right now, virtually all the funding comes from Natura Resources. Early on in the project, we had some foundation dollars to help support this. And we have gotten a few grants from the Department of Energy to do very targeted research applications.
Gotcha. So 100 million, I know there are a number of many other nuclear startups. So TerraPower, backed by Bill Gates, who would be a good guy for you to talk to, I suppose. He could probably afford to write the check. But a lot of venture capital is going to other companies, X Energy, Terrestrial, X Energy. They're getting a lot of VC money. So it could be that you're going to go to venture capitalists as well then for this kind of investment?
I think that's Natura Resources question of where they want to raise the capital. So I'll defer to Natura Resources to answer that. They obviously have listened to a lot of people and are open to ideas, but at the same time, this is something that their current investor pool believes in, and they've raised the money we've needed to keep us moving full speed ahead thus far.
Gotcha. So 100 million for the reactor. What are the biggest line items in that? I know you're going to have steam generators, right? Because you're going to be producing power. So that's kind of an or are you? Or are you going to?
Yeah. So let me back up real quick there and
Sure.
just say the NRC's definition of a research reactor limits us both in total thermal output and on what we can do with that thermal energy. And so we're not allowed to produce electricity and hook it up to a grid, and we're maxed at 1 megawatt thermal. So this research reactor is really a research project on collecting data about how this advanced reactor will behave. And so if you look at how most research reactors, there's about 30 of them around the nation. What do they do that's research? Mostly, they use the reactor as a source of neutrons and do research and use the reactor basically as a neutron source. They're not hooked up and making electricity. They're not asking, how can we get this thermal energy from fission on the grid? They're really using it as a neutron source.
Okay.
This reactor, not so much just a neutron source, because if you just want to expose something to neutrons, well, go to University of Texas. We already talked about they have a reactor doing that, or Texas A&M, MIT, Missouri, the list goes on and on. But if what this reactor will do will research how a reactor cooled with molten salt behaves. And so there's some technical differences there, and we are going to try to make sure that models that we have that simulate it and our expectations are matched, and therefore support licensing of a larger commercial molten salt reactor. And so that's really the research focus of this reactor, not can we make thermal energy, and once we have thermal energy, can we convert it to electricity? And so that's not something we have in our $100 million budget.
I got you. So then the idea would be you prove up this technology and then you could scale it up to 50 megawatts, 100 megawatts, whatever that prescription is. But at 1 megawatt thermal, in theory, if you were going to produce juice, so you could produce maybe 300 kilowatts, right? Something like that, right? 300,000 watts, or a third of the thermal output could be converted to electricity if that was what you were aiming to do.
That's right. No, the one thing I'd say that's a little different there is because we have a high temperature operating reactor, theoretically or practically, we probably could get closer to like 45% of that thermal energy converted to electricity because we're operating at higher temperatures. So again, instead of being about 30%, 45, that's this 50% increase in the electrical output from the same thermal output because we're operating at higher temperature. Another advantage of this technology.
Right. Well, so just for people who are listening, I think I understand this, and I'll use the word enthalpic efficiency. Am I right there that is the term of art? So if you have a higher outlet temperature, you can create supercritical steam, and therefore you at a higher temperature steam, you have better enthalpic efficiency. You convert more in thermal energy into electric energy. Is that, do I have
absolutely correctly
my terms correct? So what is that temperature then? Are we talking 700 C? What is that temperature?
Yeah, about 700. Maybe the output might be just underneath that 680 or something. But somewhere around that, say 650 to 700 range. Okay.
So there could be a potential, because I've talked with other people in the nuclear space, and Brett Rampal, I talked to him. He's for the podcast. He's talked about this issue of these reactors, next generation reactors. yes, we can produce power, but the one of the first opportunities may be for commercial heat, right? And that's just one of the things that's interesting about X Energy and Dow, their deal, because it sounds like Dow is saying, well, we want to use those molecules that gas to produce products. We don't want to burn them to make heat. So then, would that be one of the potential? Let's talk about markets then for this commercial molten salt, the molten salt design. Are you, I mean, longer term? I know you're in the academic space, but Natura is obviously thinking about commercialization. Are they looking at the power market? Are they looking at the petrochem refining market? Where do you know what their aims are?
Yes, we've hosted potential customers of this technology from several of them are very interested in the high temperature process heat, and for the exact applications you're talking about, plus things even as mundane as desalinating water, producing synthetic fuels, the production of hydrogen, et cetera, right? All those are more efficient at high temperatures. And so if you can provide that, 700 degrees centigrade type of process heat, then you can avoid burning a lot of hydrocarbons.
Gotcha. So talk to me about the molten salt design, and what is that fluid when you talk about molten salt? And I'm asking this because I honestly don't know. I mean, I've followed the nuclear sector pretty closely, but when it comes to the different chemistries and how they actually work, I'm a little out of my depth. So how does this work? I mean, can you just design, talk us through what this loop, instead of sending water to cool the machinery, you're using a molten salt liquid. What is that salt dissolved in? You're using uranium? How enriched is it? Talk to me about that, if you would.
Sure. So there's really sort of two things that are technically different than the current deployed commercial reactors. And the first thing is that instead of circulating water through the core to remove the heat that's generated in the core and take it to a steam generator, we're using a different fluid. Okay. The problem with water, and water is great, except that as soon as it gets up to 100 degrees centigrade or 212 Fahrenheit, it doesn't want to be a liquid anymore. And so it wants to become a steam. And now steam is not very good at moving thermal energy from point A to point B. And so to keep it as a liquid, we put it under very, very high pressure. And if you keep it under very high pressure, then you can keep it as a liquid. Well, the danger of having a high pressure system that if you ever have a leak, immediately wants to flash to steam, it gives us a lot of our driving safety factors or hazards. And so you think about what happened in Fukushima, the release of radioactive material was because the high pressure in the system, and needing to release that pressure, you vent a little bit of the water off, it immediately becomes a steam, and it wants to move up in the atmosphere and drift around the globe. And it's a beautifully designed mechanism for distributing radioactive material around the globe. Put radioactive material in high pressure water, a little leak, and let it go. So,
but you also have the risk to the personnel on site, right? If you have a leak of high pressure steam, they could get killed right on the spot.
Absolutely. The driving danger of these big commercial power plants is really the high pressure, or exactly what you're talking about. And to prevent against that, we have very, very elaborate systems that have a very high cost. And so you have to have these huge containment domes and things like that drive the cost up. And all this is related to the fact that your water wants to become a steam. So let's not use water. So what are our choices for a fluid to circulate through there that are really good at moving thermal energy from point A to point B, but never wants to become a vapor? And therefore we can operate at very, very low pressure. And so one fluid that's really, really good at that is a salt. Now, when we think of salt on our table, right, sodium chloride, we always see it in a solid form. Well, that's because it's a room temperature. It turns out that sodium chloride, if you raise the temperature up above 800 degrees centigrade, it actually can melt and it becomes a liquid. And when salt becomes a liquid, we call it a molten salt. Gotcha. Now, we're not going to use sodium chloride in our reactor. We're actually going to use a mixture of different salts put together, and the melting point is closer to 450 degrees centigrade.
What are those salts, if you don't mind? Talk us through the chemistry there.
Sure. So most people are thinking about using salts, either talking about fluorides or chlorides. We're talking about using fluoride salts, so a combination of lithium fluoride, beryllium fluoride, uranium fluoride, which brings us to the second point. In addition to using our coolant being a molten salt, the other thing we're doing is we're dissolving the fuel, the uranium fluoride, in the salt. So imagine your sugar dissolved in your coffee cup. It's in there, but it's all mixed out through it. So current technology, we put uranium behind a metal cladding and fuel rods and fuel pins, right? So we have this solid fuel rod. And the way we keep radioactive material away from people in the environment is we say that cladding around the fuel rod is the first barrier. And so as soon as that barrier becomes potentially nearing end of life, we take that fuel rod and we call it, instead of useful to us, we call it waste or spent nuclear fuel.
Right.
And in that moment, we've taken what it really is like 95% of the energy content potentially, and we've thrown it into the waste bin. And so traditional reactors use 3 to 5% of the energy content and then generate a lot of waste because 95% of the waste is fuel that we're just not using.
I got you.
And so if we dissolve our uranium in molten salt, so we have a liquid fuel instead of a solid fuel, our barrier is the barrier around the salt. That's what keeps the radioactive material from getting to the environment. Now it's low pressure, so it's not like it's wanting to if there is a leak, it doesn't spew into the air, it drips to the ground. So literally you have a catch pan and it drips to the ground. And as soon as it comes down to 400 degrees centigrade, it's a solid. It's not going anywhere.
I see.
And so by the time it gets down to the room,
may I just quickly interrupt, because
please.
there are two things that are interesting there about the cooling, and I'm just thinking about, as you're talking about this heat exchange, you need this medium as a heat exchanger between the reactor and the steam generator, right? The way to move that out. So gas would be the other way to do that, right? To remove some of that heat, right? Which is X Energy's design. And then just one other idea, I wanted to touch on this because my father-in-law is a chemist and he's walked me through many of these things. He's been Paul Rasmussen, he's emeritus chemistry professor at U of M. We were talking about this the other day and he talked about beryllium. So I just want to get this on the table because he said, yeah, okay, well, molten salt, that's a good idea, but beryllium's a nasty substance, right? That you have to be very careful with, highly toxic. Is he on the right track there? That's a problematic ingredient in this mixture. Is that a fair assessment?
Well, absolutely. Fluorine's a nasty thing, right? Chlorine's a nasty thing. One of the beautiful things about salts is they're very, very strongly bonded, right? And that's sort of, again, the chemistry of this that prevents, why does the salt not want to become a vapor, is because, again, those ionic bonds are pretty strong. And so the beryllium is a hazard by itself. And so we will treat, when we put beryllium salt in the reactor, we will be mindful of that and be careful of it. It's one of these things that you can develop a sensitivity to. So in and of itself, beryllium is much less hazardous than, say, fluorine or something like that.
But if they're bound together, that risk is much less.
That's right. Absolutely.
Okay, good. Well, I'm glad to just it's something I didn't understand, and Paul Rasmussen, my father-in-law, just mentioned this the other day, so it was top of mind. So I've interrupted you now, but so you've got this mixture of lithium fluoride, beryllium fluoride, uranium fluoride, working as this I'll call it the heat exchanging mechanism, right? But the fuel is also the thing that is producing the heat, right? The coolant is also producing the heat. Am I getting ahead of the game here?
Well, yeah. So when the salt with the fuel embedded in it is in a configuration to sustain a constant chain reaction, nuclear chain reaction, then fissions are going to occur and heat's going to be released. And where in the region designed to do that is the core. Okay, so it's a special design place. Again, we can get more technical, but most reactors, you take a neutron, when fission occurs, the neutron is moving very quickly. It's at high speeds, and we call it a fast neutron. It has a lot of kinetic energy. And when it's moving that fast, it's very, very rarely will it ever be absorbed by another nucleus to cause fission. And so most reactors, we have a moderator present, and moderator is something that allows the neutron to bump into it, exchange, and lose some kinetic energy. And after it bumps into enough of them, it's moving very slowly. And when it's a slow-moving neutron, we call it a thermal neutron. When it's moving relatively slowly, there's a very high probability that it gets absorbed by another fuel nucleus and fission occurs again. And so it's actually hard to have sustained fission. So we have a very special shape, or most generally it's a roundish looking or a cylindrical looking core, and there has to be moderator present. And if you have all that right, then you can eventually get a sustained chain reaction. In reactor talk, we say the reactor goes critical, which just means it's producing the same amount of heat each second, and that's where it likes to operate. And so when the fuel in the molten salt leaves the core and circulates through a pipe to a heat exchanger, right, where maybe steam is produced for a steam generator to go turn a turbine. When the fuel leaves the core, it no longer is in a configuration to go critical.
Gotcha.
And so fission is not occurring in a sustained way anywhere except inside the core. And that's the safety feature of this also, in that if you want to shut down the reactor, you just drain the core, and the fuel is drained out of the moderator and the critical configuration, so it's impossible for it to go critical. So you never have to worry about what happens if the reactor goes critical or supercritical and you can't cool it, because you just drain the fuel from the core, and it naturally will cool down and be safe in its sort of drain tanks.
Gotcha.
And so inherent safety baked into this type of a reactor design.
Well, and that's the key, isn't it? I mean, if we're going to get this next generation of reactors on stream, they have to have these passive kind of safety features, right? This is one of the big barriers that's been in place now for a long time. But let's talk about getting this approved, because now it's just a few days ago where the Nuclear Regulatory Commission gave the design approval for NuScale's light water design, which is briefly the shrunken version of the existing light water reactors we're using today. But it took NuScale 6 years. They first applied in 2017. It took them 6 years to get this design approval for the reactor, which is very similar to the reactors we're using now. And they had to pay on the order to the NRC something on the order of $500 million. In addition to spending, what I understand, estimates of $500 million themselves, 2 million pages of supporting documents, 12,000 page application. And I've talked about this with many people, other people, including Brett Rampal, on this podcast, about that hurdle itself being an almost impossible thing to overcome for any kind of entity, whether it's a research reactor. Anyway, it's a very long introduction, Rusty, to how do you overcome the NRC as a hurdle for this, to make, not just to get your approval of the construction permit, but then the design permit, and then to then potentially bring this into the marketplace. How do you see this? How do you see your entity and Natura and ACU overcoming the NRC roadblock, which is what I think is pretty much the right answer?
No, listen, for the
right description, rather. Forgive me.
Yes, I think that's right. I think that's an accurate description. When you look at the past and you say, how long has the Nuclear Regulatory Commission been in existence, and how many new reactors and how many advanced reactors and how many, how susceptible has that regulatory agency been to new ideas and innovation in the nuclear field? And, I think roadblock is an accurate description. And so several things have happened. I think there's been legislation passed that says, "Hey, can we modernize this? Can we look at there's a cost of not licensing new reactors, right? I mean,
yeah.
you look here in our state of Texas. We know when we had this huge freeze in February a couple years ago, there was millions of people without power for many days. Hundreds of people died. That's a real cost of not having reliable power on the grid. And so there's not just a risk of doing something, there's a risk of what happens if we don't do that. So, but how are we going to get through this? I think that the NRC is changing and is working on this. They recognize this challenge also, I believe, and they're working on it. Abilene Christian University and Natura Resources, we looked at this same roadblock, and we looked at NuScale and other companies and said, what is their success? And are we just going to jump in and try to do the same thing? And well, we don't have $1 billion to try to get a license to get started. And so one of the decisions we made early on is, can we take a smaller step? Do we have to go straight to a commercial reactor? Or can we make it easier for the NRC to license us? And what does that mean? Well, let's start with a research reactor instead of commercial reactor. And so why is Natura Resources sponsoring the construction of a research reactor at Abilene Christian University? It's not that not that they're more charitable than other advanced reactor companies. It's that they looked at it and said the best way to us to get to commercial deployment is to start with a reactor that's easier for the NRC to license. And so let's make it a small power, which means we have less fuel loading, which means we have less radioactivity. So we've just lowered the bar for everything. And so, we talk a lot of times about, we're not doing fast pitch baseball. We're not even doing slow pitch softball. We're trying to do T-ball, right? We're trying to make it as easy as possible for the NRC to approve what we're doing. So we went back and we're building off of the molten salt reactor experiment from Oak Ridge in the 60s. And we're trying to do something very similar, but we're even making it simpler. Let's go order of magnitude lower power. Let's not use high enriched uranium. Let's go to low enriched uranium. Let's where we can simplify it, let's do that. But that will give the NRC experience at licensing something that's cooled by something other than water. So first time the NRC has considered licensing a molten salt reactor. And so we're just trying to make as small a step as possible.
I got you. So, okay, right. So Rod Carew made a great career hitting singles, right? So you're not aiming for the home run right away. You're taking this intermediate step. But talk about the you mentioned Oak Ridge. So this reactor design, I know several other companies are using designs that have been tested by the DOE in the past. You mentioned Oak Ridge. So this molten salt design was tested at Oak Ridge National Labs in the 60s?
Yes. So 1965, 1969, the molten salt reactor experiment, MSRE, operated. So 4 years of operation. So they got thousands of hours, multiple fuels, a lot of good data and a lot of experience. Obviously, they didn't have the sort of scientific instrumentation around it that we would have liked. And so, you can argue, why are we building something 10 times smaller than what they built in the 60s? Well, in the 60s, Oak Ridge didn't have to go through the NRC. So going back to our previous discussion, can we get something licensed today?
Right.
And so that's where we're starting is a small step. But
and those documents are those documents easily? So I know the government generally keeps good records. So the design records for that reactor, they're easily available. Are you using those as kind of your blueprint then for the design of this?
So in a lot of ways we are. The documents are available. They're out there publicly available, and you can get to them. Now, that doesn't mean that every question you have you can find the answers to. Even though there's thousands and thousands of pages of reports out there, there's some things that they just didn't have the instruments to monitor, or they weren't concerned with. And so there are things that we wish were documented or had been learned from that experiment that weren't. And so there's value in what we're doing, I guess, in terms of the reactor we want to build. We will learn more than we have current understanding of, but we're certainly building off of that experience from 50 years ago as much as possible.
So I'm just curious to follow on that, because then you're looking at those, I'm assuming there's some blueprints for the design of the thing itself, right? The reactor itself. So you're handing those off to I'm assuming an engineering design firm and saying, here, use these, and then they're working from those blueprints in CAD or something else. I'm just curious what are the mechanics of that?
Yeah. So we're not taking the 1960s reports and handing it to an engineering firm and say, build us one of these. We have used that general design, for example, a simple loop, right? The core, the salt goes to a pump through a heat exchanger back in the core. Oh, and there's a drain tank beneath it, right? So that concept we are using. Now, we've modified it and tried to, where we can take advantages of advances over the last 50 years or better ideas, we're trying to take advantage of that. But at the same time, where there could be uncertainties about the interaction. So our choice of salt and moderator, we're taking from there. So
okay.
we're sort of do we know that fluoride, the lithium fluoride, beryllium fluoride, uranium fluoride will work in a reactor with graphite as the moderator? Yeah, we know that because they did it 50 years ago. Does that mean we're giving them the dimensions? No, we've done our own calculations of what dimensions we need. Yeah, they line up and they look very similar, but remember, we're using different enriched uranium, right? We're not using high enriched uranium. We're not using some sort of military grade uranium. We want to use low enriched uranium in this reactor. And so that means we need to change the neutronics are slightly different. We need to do some new calculations. And so we've done that. But we have taken our conceptual design. And last year we partnered with Teledyne Brown Engineering, and we gave them our conceptual design and said, can you advance this to a design where we can actually be prepared to step into a detailed engineering design? So that's where we are in the design process as we have a fairly well advanced design in conceptual levels, and we're ready to take that and produce sort of construction drawings out of it.
I see. So you've got the conceptual designs, but you're not drawing up the construction design or the actual what those blueprints for what the reactor would look like, not quite yet, but you have an idea of what it would look like, dimensions, and so on.
That's right. And I would say we're in negotiation with engineering firms that to enter into a contract for them to do that detailed design. So we have a request for proposal that it's out to many of the best engineering firms that are reviewing that and trying to give us their estimates, both time and dollars, to work with us to generate that.
So it's a fairly select group of vendors, wouldn't it be? So you've got Sargent and Lundy maybe, or Bechtel, or I know Sargent and Lundy does this kind of work. Who would be the other? I'm not asking you to. Well, I am asking you how big is that universe of people of entities that could do this? Half a dozen firms.
Yeah, half a dozen. We've had serious conversations with half a dozen that are interested in working with us. And so the folks that you mentioned, United, again, Teledyne Brown Engineering, Jacobs,
Bechtel, Brown and Root. I don't think that.
Zachary Engineering, Zachary Nuclear, also here from Texas. So, and yeah, I shouldn't have started the list without having the full list.
No problem. But you also said in one of the press release that Abilene Christian put out, said if the NRC is able to approve this application within a year, which we talked about how that might happen, might not. Nextra should be well positioned to complete the Natura Resources sponsored research reactor by 2025. And we're 2 years away. Pardon my tone of skepticism, but it's well earned. I ran into the guys from NuScale and Idaho National Labs or Idaho Falls 10 years ago. I said, blue sky it for me. When are you going to have this reactor online? They said 2025. Now they're saying 2032 something. Is the 2025 timeframe? I mean, is that really doable, Rusty?
Yeah. Well, so embedded in that quote was, hey, can the NRC review this construction permit in 12 months? So right. They've accepted it, docketed it, and said, we will review it, and we think it's going to take 18 months. So already I would say that, and listen, the NRC has never licensed anything that quickly before. So if they do it in 18 months, this is better than ever done before that I'm aware of. And so we were very aggressive and put forward a very aggressive schedule, both for us and for them. Likely, again, if they perform as they say they're able to, then that'll put us sort of 6 months behind of where we were when I made that statement. And remember, this is a two-stage licensing process. We ask for a construction permit, and then once we get permission to build it, then we can start building it, but we then have to give them an operating license, and the NRC has to review the operating license, say, can we actually turn it on? So it's this two-stage application process. And so when we get a construction permit, we're just halfway there. And so we have to go through another review process. And so if that review process is another 6 months longer than what we planned, then all of a sudden we're a year. So is it likely that 2025 doesn't happen and it's really 2026? I would say 2026 is still a victory and still a very, very aggressive schedule for any of these projects. We are in the process of trying to understand, since we just learned this 18-month review period from the NRC just really a couple months ago. We're trying to understand our schedule. Is there a way that we can still talk 25? Is really 26 the right number? So we're looking at that and trying to rebaseline that. But you're right. This is a very aggressive schedule.
Well, so as I think about this, one guy who has made a lot of money said, you have to understand where your risks are. So as I look at it and I think about, as you're telling me this, you have technology risk, right, on the reactor design itself, right, which some of that's been de-risked before with Oak Ridge.
Mhm.
but you have capital risk. Well, you're not borrowing the money, but you have a lot of capital you're going to have to put up just to get into the batter's box, right? But is your regulatory risk the biggest risk that you face in terms of how you handicap and understand where your risks are? Is the NRC your biggest risk factor?
That's certainly one of the big ones, right? I
Okay.
mean, and you know, and as we knew that stepping in, and I will say, compared to where we were 3 years ago, I think that risk has decreased. I believe that the NRC has demonstrated a commitment to working with us, and their 18-month review commitment shows commitment for them to do something better than they've ever done it before, faster than they've ever done it before. Let's talk time specifically. And so I think there's real improvement there. So while it's still one of the big ones, I'm more optimistic that there's a path forward than I was 3 years ago when we started this project.
So 3 years ago you started. So we're 2023. So when you started in 2020, but and you're still optimistic. I'm just going to double check you here after knowing it took NuScale 6 years, but that's a design permit that they got, right? And you're saying you only need the construction design, you need the construction permit and the operating permit. You don't need a design permit. Is that are you able to skip this? You're able to skip that step because it's a research reactor?
That's right. There's multiple licensing pathways. So if you really dig into the laws that govern how the NRC is allowed to approve things, there's a couple different pathways.
Which is 10 CFR 50, 10 CFR 52. Am I getting too wonky
here?
You go.
You got all the right letters.
Know my federal code here.
There you go.
That's
you do, and you know, I don't naturally speak code of federal regulation, but there are these different paths. We're going through the 10 CFR 50 path, which is sort of this construction operating license. The 52 is attractive to a lot of commercial plans. You know, again, you have a better understood and defined technology, and repeat licensure of it, I think, is a little bit easier. And I won't talk more about that because I'm not an expert, as I already said. We're going down the 50 path, which is this sort of give them a construction permit, then that gives you permission to build the reactor, and then you have to submit an operating license, and that is what gives you permission to essentially load fuel into that reactor and turn it on.
I got you. And I'm somewhat, well, I'm passingly familiar with this because TerraPower, I believe, is following the same 10 CFR 50 pathway for their natrium reactor in the one that they're planning to build in Wyoming. And I heard Chris Levesque talk about this when the IAEA meeting in Washington back in was it October or early November? I don't remember now. But let's talk about fuel. So you mentioned, you're talking about FLIBE, which is the acronym for lithium, fluoride, beryllium, uranium, I'm guessing here. But so do you need a HALEU, high assay, low enriched uranium for this? And if so, where are you going to get it?
Yeah, so we're using low enriched, not high enriched, but we are wanting to be real close to that borderline, right? So that's that high assay, low enriched uranium, or HALEU. And where are we getting it from? So another advantage of being a university research reactor is that a long time ago, back in the Atomic Energy Commission, the decision by the federal government was that we'd prefer universities not to be owners of enriched uranium and have to worry about securing it and disposing of it. So the Department of Energy stood up the Research Reactor Infrastructure Program. And so this is a program that provides fuel, and then at the end of life, retains fuel from these university research reactors. So,
your vendor for the fuel would be the DOE.
That's right.
And so I had no idea. So and just, you said low enriched. So HALEU is what, 15 to 20% enriched? Am I remembering correctly? So yeah, what is your enrichment level for? And is it called LELU or just low enriched uranium? What is it?
No. So we're trying to get real close to that 20. So 19.75, for example, right? So yes, we're in the HALEU range. So and everyone knows, or if you're following the field at all, there's a lot of concern about where we get this, because we don't have a domestic supply for this, domestic commercial supply for HALEU. We can enrich domestically, the current licensing facilities get it up to 5% or something like that. But if we're trying to get to 19%, then where do we get that? Well, the Department of Energy has a variety of sources of that fuel. Now, the request by vendors exceeds what's currently available, and that's why a lot of funding that was included in some of the recently passed legislation was for specific dollars to go to the Department of Energy stand up this reserve of high-assay low enriched uranium. We need a very small quantity compared to bigger reactors. The TerraPowers or Kairos and these other large X-Energy that are building larger reactors. What we need for a 1 megawatt reactor, university research reactor, is a much smaller quantity of uranium. And we've identified a few sources that are present in national labs, and we're working with Department of Energy to understand it. But so while the Department of Energy provides fuel for all the other research reactors in the country, right? MIT, UT, A&M, Missouri, all of those, they provide the fuel, and at the end of life, take it back. We've asked, hey, will you do that for us also? And we actually asked that question before we started this project. In fact, there's no use us going down this path if we don't have fuel. And the agreement was, yes, we want to work with you, but you're also asking for something we've never done before. So it's going to take some collaboration. And so we're working with Department of Energy to secure and identify the source of the HALEU. And then not only that, but how are we going to get that HALEU mixed in with the FLiBe in this new fuel form? It's not a solid fuel rod anymore. It's a different fuel form. And how do you transport that fuel form? Well, it takes a different types of container, and so that has to be approved and vetted through the Department of Transportation. And so there's a lot of things that have to happen to get the fuel to us that's a little different than what they've done before, and they being the Department of Energy. So we're working with them and in conversations.
Well, that's interesting because now you're bringing another wrinkle here I hadn't even thought about. But so as my checklist is right. So you got the NRC, you have to have them on board and fully cooperative. Department of Energy on board, fully cooperative, and now the Department of Transportation fully on board and cooperative. Any other? I'm not gigging you here. I'm just trying to make sure I understand. Are there other federal agencies that you're going to have cooperation from on this?
Well, I mean, certainly EPA is going to have an environmental assessment or environmental review of what we're doing, and so there is an EPA part of this that because of the environmental impact or potential environmental impact that they have to do a review of it. And so that's another agency that will certainly be involved.
And that's federal. Now we're also going to have to talk then about, as I'm just thinking out loud here, then you've got Texas Department of Environmental Quality, right? Texas DEQ. Well, I guess with Texas Department of Transportation, they would have some say in this as well then because of DOTs or the federal Department of Transportation would be involved. Is that what do you think? My impression is, given what I know about Texas, that the regulatory regime in Texas is not going to be as onerous as the federal things that you have to work out. But do you see hurdles at the state level?
I mean, certainly there will be aspects of it at a state and even local level, right? I mean, if you want to, as we travel around big cities all the time, say hazardous cargo has to take this loop, right? So the routing of materials through, is going to have some local impact and state impact. And going back to your original or one of your earlier questions, what are your major concerns, right? Obviously, NRC licensing is one of these big hurdles. Department of Energy getting us the fuel, that's a major hurdle. I think these transportation, environment, et cetera, those are things that have to be addressed. But I see those as lower risk and necessary, but probably not the same level.
Yeah, fair enough. I'm glad you put it that way because I would think as you've talked about it that obviously NRC is your primary hurdle, and then you heard I'm sure TerraPower said they were going to delay the rollout of the natrium reactor because they couldn't get HALEU, and you have a lot of other companies or entities rather that you're competing with for a limited supply of HALEU at a time when the Russians are really one of the major suppliers of HALEU. And if it's to be believed, the Russians are going to be out of the game. So then you're going to have to rely on Centrus Energy or some other outfit, a U.S. company or if Canadians, someone else to provide the HALEU. So these are other things that are going to have to be overcome. But back up just for a minute, Rusty. So I saw you got your doctorate in physics. What was your focus in your doctorate? And now you're a nuclear guy. How did that happen?
So my PhD is in nuclear physics. And
it is in nuclear physics. Okay.
It feels a little related. And I also was an instructor at the Navy's nuclear power school. And so I have some experience with military or the Navy's nuclear program. And so. And
are you a former Navy guy too, or no?
Yeah. Yes.
Oh, okay. So, I think it's worth noting because the electric power sector is just filthy with nuclear, Navy guys of all kinds, nuclear Navy guys, just power plant. The Navy turns out some of the top people in the electric sector and has been for decades.
Mhm.
So you were in the Navy and then went back to school to get a PhD in nuclear physics. Then was that your
Yep,
pathway?
that's right.
And are you from Abilene?
Yeah, so I grew up Abilene High School, and I got my undergraduate engineering physics degree at Abilene Christian University, and then I went off to the Navy, taught the Navy's nuclear power school, then University of Texas for my PhD in nuclear physics, and did some research at Fermilab. Had a postdoc at Los Alamos, worked at Brookhaven National Lab before I came back here as a faculty member, and been here for 22 years now.
Gotcha. So when I just have to ask. So when you were in the Navy, did you spend any time on ships, or you were mainly in the educational part of the Navy?
So mainly in the educational part, and for people that are served long term, like my father and others, when they talk about sea time, they measure it in years. I can measure my sea time in hours. So
Okay.
I was there, but embarrassingly, it was a short period of time.
Well, look, I'm not saying no, I don't think it's anything to be embarrassed about. I'm just curious because that was one of my heroes in the nuclear or in the electric sector is Frank Sprague, and I have a chapter about him in my book, and he was one of the people that we profile in Juice in my documentary. And Sprague went to the Annapolis, and he learned about the electricity in the Navy, and that was one of the things that set him up for success when he later worked for Edison and then went out on his own and perfected the electric streetcar, perfected the electric elevator. But I digress. So let's talk about ERCOT for a few minutes. We're coming up on about an hour, and a quick station break. My guest is Rusty Towell. He is the director of Next Lab and a professor in the Department of Engineering and Physics at Abilene Christian University. You can find out more about him at acu.edu/next. That's acu.edu/next. What about ERCOT? Do you see a pathway? We've talked about other hurdles. ERCOT is a complex market. I will think that I can say that with no fear of being contradicted. They're rolling out this new thing called the performance credit mechanism, which the Public Utilities Commission is saying, well, this is going to help stabilize the grid, et cetera. Have you followed this at all, the ERCOT politics, and do you see the potentially molten salt reactors or other reactors being able to compete in the ERCOT market?
Yeah, so I think ERCOT kind of came on my radar screen when we had the huge freeze 2 years ago, right?
Right.
And that's when I learned that acronym and who they were and what they're doing. So I am no expert on the business management of that system.
Yeah.
What I'm very confident in is if you can bring a source of energy that's reliable, safe, efficient, and at a price point that doesn't require subsidies or mandates, but it can actually compete in the marketplace at its own levelized cost of electricity, that if you bring that forward, it'll be embraced, and not only by ERCOT, but I think by utility producers around the world.
Okay, well, I'm glad you brought that up because that brings to mind another question. Then, so what are you thinking you could produce? I mean, blue sky this for me. And I asked people in the nuclear, okay, blue sky this for me. And like I said, the NuScale guys, when I saw them in Idaho Falls years ago, blue sky it for me. When are you going to have this deployed? So blue sky it for me. You get this design, you get the construction permit, you get the operating permit, you get the ability to potentially then to go commercialize this. What could a molten salt reactor, what could you be producing power for if, say, you had a 100 megawatt, 50 megawatt reactor and you can scale this up? What price point could you meet on a kilowatt hour, megawatt hour basis? What have you done those numbers?
So we've looked at those numbers and just said, what's possible, and really you can just take a few factors and compare it with current deployed nuclear. And what you find out is that we have a levelized cost of electricity that comes in slightly lower than natural gas. Okay. And all we've done is we've taken credit for just a few things that we don't need that huge dome over the top. So you take the levelized cost of electricity of current nuclear fleet, so heavily regulated, a lot of safety features, type of technology, and you say, let's just strip away the 40% cost of that containment dome, right, that you no longer need. And then let's say we don't throw away 95% of our fuel into a waste stream, but we use 100% of our fuel. And we're operating at higher temperature, so we get more electricity for the same amount of thermal energy. And if we just consider those three factors, all of a sudden it takes what is an expensive form of electricity, current nuclear, and drops it down cheaper than natural gas.
So you're saying then, and I think I'm pretty familiar with these numbers, that you could be producing power at $20 to $30 a megawatt hour. I mean, that would be competitive with nat gas now, right? Where nat gas is at $3 right now, $3 per million BTU. So might be a little bit less than that, but $20 to $30 to even $40, and that would seem to be the sweet spot in the market. You're saying you could meet that market, that price point.
That's right. That's what we believe. And now, again, that's for an nth of a kind, right? I mean, we're not talking about the first commercial deployed one. A first of a kind always has bigger expenses, and so we're really talking about an nth of a kind. But we believe that that's possible.
Is there a sweet spot in terms of that design in the size of an SMR? We haven't put that acronym out there, small modular reactor. In terms of the marketplace, I know you're much more on the physics and the academic side than the commercial side, but once you scale this up, are you thinking a 30 megawatt reactor, 50 megawatt? What is that? What size of the deployable reactor are you thinking would find purchase in the marketplace?
Yeah. So we've looked at what is deployable in a small modular reactor form. So what could you mass produce in a factory and then put on a bed of a flatbed truck and deploy? And the thought there is we could probably do something up to about 250 megawatts thermal, or an order of 100 megawatts electric, as being sort of the sweet spot for Natura's first sort of commercial deployment. And so we've looked at that deployment scenario, and as we've talked to different potential vendors, right? So electricity producers, but also users of that thermal energy, they say, yeah, that's useful, right? And if we're a large plant and we need two of these sort of modules, great. We'll invest in two modules, and that would get us, 500 megawatts of thermal energy or 200 megawatts of electricity, or in a lot of applications, it allows us to do both. You could imagine a scenario where you deploy and you both desalinate water and produce electricity. Right. When there's high demand for electricity, you produce a lot of electricity. When you're off peak, you run the power plant at full power, but you produce less electricity, but you start desalinating a lot of water. And water is easy to store pure water for use later. And so that allows you to operate the reactor the way it likes, sort of constant power, but also meet the changing electricity needs.
Gotcha. Well, that's interesting because this is one of the big debate now in the SMR world is what's the right size? How soon can we get it deployed? What it's going to cost? What are the hurdles? And there are so many different pieces at play here. But is it the cost of natural gas that you're competing then with fundamentally in the U.S. market? I mean, it's different in Europe. We're going to talk about $3 gas today at Henry Hub versus, I haven't checked today, but the TTF's probably at 15 or 20, something like that. Is the cost of gas going to be, is that going to be the competition? You mentioned that, right? That we think we could produce, you think you could produce power for less than the cost of gas. So that's your real benchmark that you have to meet. Is that a fair?
Nature Resources talks about sustainable energy, and sustainable energy to them is not only environmentally friendly, what comes to mind a lot of times, which it is, but also it survives in the marketplace without this mandates or subsidies, right? So we're allowed to, if it's just a flat open market that's level playing field, and if you want to deploy, to where there's real growth need for electricity in third world countries where they need energy to really raise the standard of living. If you want to deploy into those parts of the world, you're not going to deploy something if it's financially unaffordable to them. Sure. So you have to be able to compete and be relevant. And we believe we can because the technology is right, that the inherent safety allows you to build it in such a way that you don't have to invest so much in these multiple containment domes for when something goes wrong, because you don't have to, that's never going to happen. It's impossible for us to spew gas up in the atmosphere if we have no water involved with the plant.
Sure. Well, good. Well, so we're getting on to an hour here, Rusty. So I'm going to bring us to an end here pretty quickly. The same questions I ask all my guests. What are you reading? What's on the top of your book pile these days?
So my number one go-to book is the Bible. When I don't do a lot of reading, but that's my number one go-to, and so I'll say that's what I've been in daily for the last few days.
Okay, well, that's an old reliable. No problem with that. Authors are some of them well known, some of them unknown. Then what gives you hope? That's the other question that I always put to my guests, and I'm always intrigued by their answers. What gives you hope?
Well, I mean, this project gives me hope, and the ability for this project to really address world needs and make the world a better place. I mean, it just for me, I prior to working on this project, I did a lot of basic research at national labs, a lot of fun questions. You know, I mean, I did my dissertation on the anti-quark content of the nucleon, right? I mean, I'm sure that's riveting to you, and you're excited to hear about that someday. But
I'm sorry, the anti-quark. Forgive me. What did you say?
well, how many anti-up versus anti-down quarks are there in a proton? And that's sort of what I study.
The answer I don't know, but anyway.
Yeah, and you know, more importantly, do you care? Or you know, the point is, it was basic research, right? It was fun discovery. It's always neat to learn about the world, but it's a better feeling when you know what I'm doing is going to make the world a better place. And you know, and here at Abilene Christian University, where we have young students coming in and just starting their choosing a professional career, and by getting a degree in the field they want, when they see how they can tie a chemistry degree into making the world a better place, or an engineering degree and make the world a better place, or physics or computer science or mathematics or whatever, but when they can see the purpose of how they can do it, then they come at the job with an additional passion that they don't have otherwise. You know, seeing that passion, excitement, of course, that gives me hope, and so I'm optimistic that we're heading the right direction, and the NRC and DOE and all these other factors will get in line, and this will be a reality.
Well, that's a good place to stop. So we'll stop there. My guest has been Rusty Towell. He's the director of the Next Lab and professor in the Department of Engineering and Physics at Abilene Christian University. You can find out more about their project, which is they've applied for the first construction license for a research reactor of any kind in the United States in more than 30 years, and they are in Abilene, Texas. You can find out more about them at acu.edu/next. Rusty, thanks for coming on the Power Hungry podcast. It's been very interesting. Thanks.
Thank you so much for the invitation.
And all you out there in podcast land, tune in for the next episode of the Power Hungry podcast. It might be as good as this one. Until then, see ya.